In this lesson, we're going to focus on drawing Newman projections of certain molecules, and we're going to discuss the relative stability of those molecules. So let's go ahead and start with ethane, CH3CH3. So how can we draw the Newman projection along the C1-C2 bond? The first thing I would like to do is expand this structure. So the first carbon, which we'll call C1, it's attached to 3 hydrogen atoms. So to draw the Newman projection, draw a circle, and at the center, this is going to represent C1, which is in the front. And so it's attached to 3 hydrogen atoms. Now behind it, which we can't see, is carbon 2, and it's also attached to 3 other hydrogen atoms. So this is the staggered conformation of ethane. Now, one thing we could do is rotate the C1-C2 bond such that this hydrogen is directly behind that one. So it's going to be eclipsed in it. So there's 2 ways in which you can draw the Newman projection of ethane. You can draw it like this. So this is the staggered conformation, or you can draw the eclipse conformation. Which one do you think is more stable? The staggered conformation or the eclipse conformation? The hydrogens in the back, I'm going to draw it in red. You need to understand that the staggered conformation is more stable than the eclipsed. And the reason for that is this interaction where the hydrogens are eclipsing each other, there's torsional strain. And so this conformation is going to be higher in energy. So this is the less stable conformation. And on the left, we have the more stable staggered conformation. Now let's move on to our next example. So let's draw the Newman projection of butane along the C2-C3 bond. So first, let's draw carbon 2 and carbon 3. Now, attached to carbon 2, which is this carbon right here, it has a methyl group on the left, and it's a CH2, so it has 2 other hydrogen atoms attached to it. Now, carbon 3, which is this carbon, I'm going to highlight that one in blue, it's also attached to 2 hydrogen atoms and a methyl group. And so we need to draw everything around this C2-C3 bond. So now let's draw a Newman projection. So I'm going to draw a smaller version this time. So this is going to be carbon 2, which I'm going to highlight in red, this red dot. So carbon 2 is in the front. And carbon 2 has a hydrogen, another hydrogen, and a methyl group. I'm going to place the first methyl group at the top, and then the other 2 hydrogens. Now carbon 3, which is in the back, it also has 2 hydrogens and 1 methyl group. So I'm going to place this methyl group at the bottom and these hydrogens on this side. So this is a staggered conformation, but it has a specific name called an anti-conformation. It is the most stable of the 4 Newman projections of butane. The reason for that is because the methyl groups are so far apart. You want to keep them as far apart as possible. And so this is the anti-conformation of butane. The dihedral angle between these 2 methyl groups is 180. Now let's draw the other conformations of butane. So I'm going to keep the first methyl group at the top. I'm not going to change that position. Now the second methyl group, we can put it right here. And so the other hydrogens will be around it. And so as you can see, we don't have the eclipse conformation yet. This is still another type of staggered conformation. However, this particular conformation is known as the gauche conformation or the gauche conformation. and the dihedral angle between the two methyl groups is 60 degrees. Now, there is some steric strain when the methyl groups are close to each other. And so whenever you have this gauche interaction when they're 60 degrees apart, you're going to have this steric interaction. So therefore, the gauche conformation is less stable than the anti-conformation. This is going to be number 1, meaning it's the most stable. This is number 2, it's the second most stable. Now there's two types of eclipse conformation that we can draw. The first one, which I'm going to show in red, a hydrogen eclipsed the methyl group, and we have this methyl group eclipsed in the hydrogen. So this is the third most stable conformation. And then in the least stable conformation, the two methyl groups eclipse each other. Now think of the sun or the moon eclipsing the sun. The moon could completely block out the sun, and that's what's happening here. The white methyl group is eclipsing the red methyl group, so technically you should not be able to see the red methyl group. It should be like directly behind the white methyl group. So this is called totally eclipsed. It's the least stable of the 4 conformations of butane. Now let's go over the angles for each one. So going back to the gauche conformation, if you notice the angles between the methyl groups is 60 degrees, or if you go in the other direction, it's 300. So there's two angles that corresponds to this conformation, 60 and 300. Now for the eclipse conformation, number 3, notice that the methyls are 120 degrees apart. Or if you count it in the other direction, they're 240 degrees apart, because 240 plus 120 adds up to 360. And for the last one, it's 0 degrees apart. 0 degrees and 360, they're the same. Now the reason why I mention that is because when drawing the potential energy diagram, you're going to see how it relates to each other. So this angle is the 0 degree angle. Here this is going to be 60, and then 120, and then this is 180, 240, and then 300, and then back to 360. So the anti-conformation is the one with the lowest energy. On the y-axis, we have potential energy. On the x-axis, it's the dihedral angle. So recall that the anti-conformation, which we said was the most stable, it had a dihedral angle of 180, and so it has the lowest energy. So this was structure number 1, the most stable. The second one was number 2, and number 2 was the gauche interaction, and it had a dihedral angle of 60 and 300, which we saw on the previous page. And then structure number 3 was the eclipse conformation, which I'll write E for eclipsed, and it had two angles, 120 and 240, which we see here. And then structure number 4, that was the least stable, so it has the highest potential energy, and it had a dihedral angle of 0, so that was the total eclipse structure, or totally eclipsed rather, and 0 and 360 are the same. So you could see where they're located on this potential energy diagram. So as the potential energy increases, the stability of the molecule decreases. Highly stable molecules have low potential energy, and unstable molecules have high potential energy. So that's it for butane. Let's draw the Newman projection of, let's say, 2, 3, dimethylpentane. So feel free to pause the video and try that, and identify which of those Newman projections, this could be many, which one is the most stable out of the ones you can draw. So first, let's draw a line structure. So here we have pentane, and then we have a methyl on carbon 2 and 3. And also, I need to specify that we need to draw the Newman projection along the C2-C3 bond. So this is CH3, and then we have a CH, and then another CH3, and then it's a CH, CH3, CH2, CH3. So this is carbon 2, and this is carbon 3. So carbon 2 has two methyl groups, and it has a hydrogen. So here's the first methyl group on carbon 2. Here's the second one, and then here is the hydrogen. Now for carbon 3, it too has a hydrogen, a methyl group, but it also has an ethyl group. So let's put that in the back. So here is the methyl group, here's the hydrogen, and here is the ethyl group. So what other Newman projections can we draw of this molecule, of 2,3-dimethylpentane? So this is carbon 1. Carbon 2 has a methyl group. Carbon 3 is behind it, which also has a methyl group. And then here's 4 and 5. So we have a total of 7 carbon atoms. So let's redraw the stuff around carbon 2, the 2 methyl groups with the hydrogen. Now, another staggered conformation that we can draw is we can put this ethyl group where this methyl group is. And so that's going to give us... Now, are these two staggered conformations that I'm drawing right now, or the two that I have on the board, are these two the same or are they different? Notice that they're equivalent to each other, because here we have a gauche interaction, the same on this side, and there's another gauche interaction between a methyl and an ethyl. So as you can see, these two structures are identical. However, we could create a different structure if we place a methyl group here and then the ethyl group here. So that's a different staggered conformation. In our original structure, we had one methyl-methyl gauche interaction. In the new structure, we have two methyl-methyl gauche interaction. And in the old structure, we had one methyl-ethyl gauche interaction. But in the new structure, we have just one methyl-ethyl gauche interaction. So in this new structure, we have a total of 3 gauche interactions. In the original one, we have 2. So this structure here is less stable than this one. Now let's see if we can draw another staggered Newman projection, because I think we can. And we can do so if we put the ethyl between the 2 methyl groups. And let's put the methyl here. So this time we only have one methyl-methyl gauche interaction, but now we have 2 methyl-ethyls gauche interactions. And because ethyl is bulkier than methyl, it stands to reason that an ethyl-methyl gauche interaction has more energy than a methyl-methyl gauche interaction. So therefore, this is going to be number 1, the most stable staggered conformation that we can draw. This is going to be number 2, and this is going to be number 3, the least stable of all the staggered conformations that we can draw, based on the idea that an ethyl-methyl interaction has more steric strain than a methyl-methyl interaction. Now, let's draw the eclipsed conformations. So let's start with this part first. And I'm going to begin by eclipsing the methyl groups together. Let's make this an ethyl group. And then this is going to be the other hydrogen. Now let's draw the next structure. So here we have an HH eclipse interaction. So now let's put a methyl group next to the hydrogen. So that's going to be different. Let's keep the ethyl group on this side. If we put the ethyl group here, it's the same as putting it here because the two methyl groups are the same. Now the only other different structure that we can draw is we can put the ethyl group next to the hydrogen. That will be different than the first two. And then one hydrogen has to be with one of the other methyl groups, and the other methyl group has to be there too. Now I'm going to leave it up to you to rank the stability of these three eclipse conformations. But just to get you started, it's good to know that whenever you have two hydrogen atoms eclipsed to each other, the torsional strain energy value is about 4 kilojoules per mole. And when a hydrogen eclipses a methyl group, it's about 6 kilojoules per mole. And whenever you have two methyl groups eclipsing each other, the energy value is 11. So we have enough information to compare these two molecules, because these two interactions between a methyl and an ethyl group, they're the same, so we don't have to take that into account. So for the two remaining groups, this has a total energy profile of 12, and for this one, it's 15, not taking the ethyl-methyl interaction into account. So because the structure on the right has a higher potential energy value, we could say it's less stable than the structure on the left. So the structure on the left is going to be more stable. Now, I'll leave it up to you to do research to determine how this molecule compares to the other two. So you need to determine the energy value between a methyl and a hydrogen, an ethyl and a hydrogen, and also an ethyl and a methyl in order to answer that question. Now let's work on some practice examples. Number 1, draw the most stable conformation of 2-methylbutane along the C2-C3 bond. Feel free to pause the video and try this example. So let's start with the line structure of 2-methylbutane. So first we're going to draw butane, and then we have a methyl group on carbon 2. So this is carbon 2 and this is carbon 3. Now let's draw everything else that's attached to those two carbons. So on carbon 2 we have another methyl group and is a hydrogen. Keep in mind carbon can only form 4 bonds. Carbon 3 has a methyl group attached to it, but it has 2 hydrogens. So let's draw our first Newman projection. So we're going to have carbon 2 in front. We have our first methyl group, and then we have another methyl group to the left, and then a hydrogen. So here are the 3 things that we've added. So now to the back carbon, or carbon 3, we're going to add these 3 groups. So I'm going to start by putting the methyl at the bottom and the other 2 hydrogen atoms here. So notice that in this particular conformation of 2-methylbutane, we only have one gauche interaction with an energy profile of 3.8 kilojoules per mole. Now let's draw another one. Let's see what other Newman projections that we can draw so we can compare it to our first example. So the first 3 groups, I'm going to keep it the same. Let's put this methyl group here. and then we can place the other two hydrogen atoms. So notice that we have two gauche interactions. So the energy profile for this particular conformation is going to be 3.8 plus 3.8, which is 7.6 kilojoules per mole. So far, we've placed the methyl group in this position and in this one. Let's see what happens if we put it there. So if we put it towards the right, the other hydrogen atoms have to go in the other position. So we only have one gauche interaction. In fact, these two conformations are the same. So those are all of the stable staggered conformations that we can draw. We know that the eclipsed conformations will be less stable, so we're not going to draw them. The one that is the most stable is the one with the lowest potential energy. So therefore, this particular conformation of 2-methylbutane is the most stable. So this is our answer. Number 2, consider the following conformations of butane. What is the energy barrier between the totally eclipsed conformation and the anti-conformation of butane? Now the energy profile for the anti-conformation, which is on the left, is basically 0. We don't have any gauche interactions, and there's no staggered there's no eclipse interactions. So that's the energy profile. Now on the right, we have the totally eclipsed conformation. So what's the energy profile for that, based using the table on the right? The table on the right gives us the corresponding potential energy for each group interaction. So here we have two CH3s that are eclipsed to each other. So the energy value for that is 11. And then we have two hydrogen atoms that are eclipsed as well. So the energy for each is 4. So if we add 11 plus 4 plus 4, that's going to be 19. So the difference between these two energies is going to be the energy barrier to rotation. So in order to rotate butane from its anti-conformation to its totally eclipsed conformation, we need to put in 19 kilojoules of energy per mole to get it going. So that is the energy barrier to rotation to convert it from anti to the totally eclipsed conformation.